Hello, everyone, and thank you for joining us today. Welcome to Megger's Virtual Motor Best Practices Seminar. My name is Michael Fleischer, and I'm the Digital Marketing Specialist for Megger. I'll be acting as the moderator for today's presentations and supporting you on any technical issues or questions for our presenters. On the right side of your screen, you will see a control panel that looks similar to this one. You can submit questions at any time during the presentation by typing in the box highlighted in red, and I will read the questions out during the Q&A segments at the end of each of our presentations today. Today, we will have two separate presentations with their own Q&A sessions, so please stick around after our first presentation concludes. Additionally, a certificate of attendance, copy of the presentations, a link to the recording of this seminar, and your Baker 10% discount codes will be sent to all attendees in 2 business days. The presenter for our first segment today is Abel Gonzalez, Applications Engineer. Also, to assist with the question and answer session, we will have joining us our other presenter today, Leslie Reed, who's our technical trainer and applications engineer. All right, let's go ahead and get started. Thank you so much for joining us today, Abel.
Thanks, Mike. I'll take it from here, I guess. Okay, guys, so today we will have 2 presentations. The first one is going to be on static testing. First of all, the title of the best practice seminar that we're going to do is rotating machines testing. It's divided in 2 days. And the first day we'll have presentation on static testing, which is the one that I'm delivering for the next hour. And then we will have Leslie do a presentation on dynamic testing of rotating machines. On these presentations, my presentation, we will go over the typical failure modes of electric motors and the failure mechanisms. And then we will focus on the typical insulation tests used for electrical motors. On those insulation tests, we'll talk about the insulation resistance, polarization index, and dielectric absorption ratio. We will mention the step voltage test, the high pot test, and the surge testing. It's where we're going to finish our webinar. So first, let's talk a bit about the typical failure modes on electric motors. Many research papers have been published, and white papers, and just different compilations of results on the industry, but they all come down to numbers similar to this ones. Depending on the type of motor that you have, about half of the failure on those motors come down to the bearings or the mechanical part of the motor. The stator is responsible for 26 or thereabouts percentage of the failure on machines. Rotor comes down to 8%, and then you have an undescribed other that's about 22%, which can be of many different types. So that's why it's not, it's typically not, let's say, divided here per the particular sites. But the most important thing is that we have a quarter of the failures of the machines that come down to the stator, and about 10% of those of the failures in the machines that come down to the rotor. If we divide by the voltage level, when we talk about machines below 4 kVs, the numbers are very similar to the ones that I presented on the previous slide. But when the voltage of the nominal voltage of the machine is higher than 4 kV, then we have that the percentage of failures in the machine related to faults on the stator increases dramatically to somewhere around 60 to 70% of the faults. Those are typically faults that have to do, when we say faults related to the stator, they're typically faults that have to do with failures in the insulation of the machine, and that's why it's so important to have a good, let's say, picture of the status of the insulation of the machine. When it comes to electrical motors, more than, I would say, 70% of the motors out there are squirrel cage induction motors, which is where most of the literature is, I would say, addressed to testing these types of motors. Here we have a typical AC motor where we present the stator of the motor, we present the rotor, we present the squirrel cage, the coils, the bearings, all the different manufacturing characteristics of the motor. And when it comes to the motor itself, what can go wrong? Well, Murphy's law tells us that if something can happen, it will happen. And the corollary number one is that whatever can go wrong will go wrong. So in a motor, you can have failure happening in every single one of the components of the motors. Of course, the most common failures that happen in the motors were presented on the previous slides have to do with the stator windings, and they have to do with the rotor, the parts of the motor that have the let's say greater or greatest amount of use. And again, I'm going to focus today on failures that have to do with the electrical system of the motor. I am not going to touch directly anyway failures that have to do with the mechanical system of the motor. The second presenter, my colleague Leslie, she will talk in her static testing a little bit about how to determine faults that have to do with other parts of the machine. But I'm going to focus mostly on faults that have to do with the electrical makeup of the machine, namely faults that can be identified doing active tests or insulation tests on the machine. I call them active tests, which are the types of tests that you do. The machine is not in operation, which are the static types of tests that we talk about, because during these tests you inject a magnitude, where it's a current or a voltage, into the machine, and you measure the results of the injection of that magnitude into the machine. You do the injection yourself. So when it comes to failure mechanisms in the machine, let's first start by how much insulation a typical machine will have when it's constructed new. Let's say we have a 460 or 480 volts motor. When that motor is built, the typical insulation capability of the insulating material that we put on the conductor has around 6,000 volts AC, which comes down to 8,400 volts DC. Remember that in order to do that conversion, what we do is we take the peak of the AC waveform, and we say that the capability for that piece of insulation to support voltage is equal to the peak of the maximum AC RMS voltage that insulation can take. Now, the slot liner in the that we put in the slot to build the insulation of the winding in the slot is typically going to have, for that 460 volts motor, around 20,000. And remember, this is when the machine is being built, in the moment when the machine is new, just out of the production line. So combined, we can say that the insulation to ground of this machine is going to be around 28,000 volts DC, which means that when the machine is built, the capacity of the machine to support voltage is way, way higher than the nominal voltage that we are going to inject into that machine. But as time goes by, a lot of things start happening to the machine. The first one that happens is that temperature takes care of damaging the insulation. For every 10 degree, and this is something that's I would say it's a rule of thumb, and of course some insulations will behave a little bit different, but in general, for every 10 degrees increase in temperature of the insulation, the amount of insulation degradation is doubled. What that means is that for every 10 degree increase in temperature, you can assume that the amount of insulation that you have is going to be divided in half. The contamination of the machine, be it chemical or be it thermal insulation causing heat to build up in the winding, be it abrasive wear of the insulation due to the impact from airflow and the flow of the air that's cooling the machine, which is something good for the machine, also brings particles with it, that those particles scratch the surface of the insulation, and little by little, remember them, those machines, electrical machines, they're running all the time, so little by little we are damaging the insulation. And after a while, remember that the amount of insulation that we have depends on how thick the insulation is. If we are little by little degrading the amount of insulation that we have, then little by little we are lowering the amount of insulation that we have, or the amount of voltage that that piece of insulation can take. Moisture, which creates a surface leakage, is also another source of damaging of the insulation that has to do with contamination. Mechanical movement, when the motors start and stop, you have vibrations that cause the same effect that I was talking about with the air. These vibrations tend to degrade the insulation. Do we have thermal growth of materials during startup, meaning that when the motor starts, the amount of current that circulates is sometimes 7-8 times higher than the nominal current. So we have a huge amount of heat that's generated in the beginning of the movement of the motor during the startup, and that creates the deposit of materials that will later create damage to the insulation. And over voltage spikes, which happen either when the motor starts or during the normal operation of the motor. If we have the motor connected, as it is the case today for I would say more than 50%, a great deal of motors out there are connected to variable frequency drives, which operate on the principle of switching millions of times per cycle in order to build the waveforms and control the motor. Well, that switching damages the insulation, and that switching can also be because of the operation of other motors that are connected to the same line, electrical noise, lightning, etc. So it's not only because of the controller that we have connected to that motor that we have those over voltage spikes. So when we put all these effects together, we have reason for the degradation or the lowering of the maximum voltage that insulation can take, and that happens over time. Now, how do we see that in the motor? Well, typically we see it in either a turn to ground fault. That's when the insulation to ground of a particular turn fails. We have a turn to turn, which is when two turns touch together and the insulation is no longer enough to hold the voltage in one. And then we have circulating currents that go from one turn to the other instead of going across the whole turn. We have also coil to coil, when we have two coils in the machine that touch together. This is a type of turn to turn, but when we're talking about turn to turn, we're talking about turns in the same coil. When we're saying coil to coil, we're talking about turns in different coils of the machine, or when we have the same thing but happening between phases, which is, I would say, a little bit different, a little bit more catastrophic because of the amount of voltage involved in the difference between one phase and the next. Now, when we have burn turns in the machine, we create an effect of, let's say, auto transformer, because when two turns touch one with the next, an effect of circulation of a circulation of current is created, which means that we have an effect of a huge amount of current that circulates between these two turns, which in turn creates a lot of heat. And that's why the initial shorting of the turns initially happens outside of the machine, but then since most of the let's say when the amount of heat that can be dissipated inside of the slot is way less than the amount of heat that can be dissipated in the let's say extension. So even though sometimes those faults begin in the extension of the winding, since the dissipation of heat is way less or way poorer inside the slot, then this fault, which starts at the ends of the winding, then it transfers into the slot because there is much less dissipation of heat inside the slot. which means that we're going to have a lot more damage inside the slot for a fault that started somewhere else. And that's why you see sometimes the effect on the inside for a fault that actually started on the outside. According to IEEE, a welded fault turns will burn through the slot liner to ground within 15 minutes. There is a video produced with this effect that I encourage you to look for it. It's very interesting. A fault is produced between two turns, and then after 15 minutes, you see smoke coming out of the machine. Sometimes it happens even faster. It depends on the type of winding that you have, on the amount of heat that winding can dissipate, if the slot is closed or not, if it's a big machine or a smaller machine. But the thing is that even though you see most of the times the failure as a ground or a coil to ground failure in the slot, most of those failures actually started as a turn-to-turn fault with the effect that I was just describing. You have two turns that touch each other, a lot of heat is generated. Now that effect is transferred into the slot, and inside the slot then you have a burning of the insulation that transfers then to a touching between that turn and the ground, and then you have a fault to ground with the effect. Remember that the amount of voltage that you have between turns is very small, but the amount of voltage that you have between the turn and the ground is typically very high, which means that even though you see that the fault is represented as a turn to ground fault, that is actually a fault that started as a turn-to-turn fault. More than 80% of the electrical stator failures actually start as a turn-to-turn fault and then degrade or let's say evolve into a fault to ground fault. Now, the possible failure modes that we have are turn-to-turn, coil-to-coil, phase-to-phase. Here we have these descriptions. You can find them. There's a lot of literature about this, and there's a lot of case studies out there that you can see, and you can find the different types of faults. But the main failure modes that we have are like this, like I was describing: turn-to-turn, coil-to-coil, phase-to-phase, coil-to-ground, and sometimes you will have an open circuit. Now, an open circuit can start as a short circuit, some welding that would happen, and then maybe a breaking of a conductor that may or may not turn into a ground coil to ground fault. It could just simply become an open circuit because of the welding effect that happened. Now, where do those turn-to-turn faults happen? Well, most of these turn-to-turn failures, they start at the early turns. When we say early turns, these are the turns in the machine or in the winding that are closer to the leads of the machine. Why? Because of the way the voltage is distributed inside of the winding when we have voltage spikes. We will see later on, I have a slide where I show the voltage distribution on the winding and how we can see that the voltage is not distributed equally or linearly across the winding. Now, on startup, we have voltage spikes. We can see them here on this figure that I have, or this graph that I have, where you can see the bus voltage, and you can see that up to 5 times the per unit. And the per unit, this is a number that you will find a lot in the literature about motor testing. The per unit volts are simply the peak of the line to ground voltage of the machine. That's why you see voltage to the line voltage divided by the square root of 3 times the square root of 2. For example, for a 480 volt, you would divide that by the square root of 3. That gives you the line to ground voltage, and then you multiply by the square root of 2. That's your per unit. And those per unit are that's the voltage that's used to describe the test voltage that you have to use on a machine. We will see it over and over across the presentation. Now, on startup, you will see a lot of spikes. Now, the voltage spikes that the machine sees can be produced and are produced regardless of whether the machine is connected to a variable frequency drive or if it's connected to a three-phase sinusoidal system. If the machine is connected to, let's say, a three-phase sinusoidal system under normal operating conditions, there won't be any voltage spikes. Ideally, let's say there is no noise in the system and whatever. But when the machine starts, when the machine is put in service, when the machine is connected to the system, there is a transient process that happens where the machine draws an amount of current that sometimes up to 7 times the nominal current of the machine. During that interval, during that process, you can have spikes of voltage that can be generated as a consequence of that startup process that can be up to 5 times per unit. For example, for this 480 volt motor where we have 392 volts, those spikes can get up to 2000 volts. And that is during regular operation and with no connection to any switching device or whatsoever. Now, if we, together with that, we put the fact that sometimes machines are connected to variable frequency drives that have sometimes they have this type of waveform in the voltages, which, as you can see, we have voltage spikes happening at the beginning and at the end of the commutation of each of the pulses that happen in these devices. And this is for a 6-pulse commutator. Sometimes we have different types of commutation. The point is that you will have many spikes happening during the normal operation of the machine. Now, those spikes affect the insulation in ways that are, I would say, still being investigated, even though there's a fair description. Last year, I was at the IEEE Electrical Insulation Conference in Calgary, and I would say that more than 50% of the papers presented in that conference had to do with the effects on different insulation systems of voltage spikes or commutated voltage producing devices. Now, the motors, they will not fail at the operating voltage where they see maybe 20 to 30 volts turn to turn. But remember what I said before, every time the motor starts, it sees voltage spikes of up to 5 times per unit. And here in this table, all we've done is for different bus voltages, we've told you what the per unit voltage is and what's the meaning of that 5 per unit. See, for example, a 600 volts will get up to 2500 volts per unit, and that's just by means of the regular operation of the motor. Now, when the motor's life begins, it will have the voltage, the voltage, the breakdown voltage, or the capacity of the winding insulation to stand voltage is going to be around 28,000 volts DC from the winding to the ground, and it's going to be a turn-to-turn insulation of 16,800 volts. Remember I said 8,400 for a single wire? Well, when you put that together, you put 2 wires together and they have twice as much insulation. That's where you get this 16,800 volts DC. Now, here you will have your bus voltage, and the difference between the maximum voltage and the bus voltage, I would say, is what can characterize the health of that insulation. The higher this difference, the less likely the motor is to fail. Now, remember that through the life of the motor, we have the motor continuously operating under conditions where it is seeing voltage spikes, and it's also seeing the conditions that we talked about before: thermal aging, we have chemical elements, we have contamination, we have aging of all kinds, and that means that the insulation of the motor, the breakdown voltage, is little by little, lowering and getting lower and lower over time until two things happen. The first is that the insulation of the machine touches the maximum voltage of the spikes. I chose to represent this here as the voltage on one of the spikes and not at the maximum of 5 per unit. But you could see that as long as you are below 5 per unit, you are in danger. And then at some point, you will have the insulation below the bus voltage, which means that pretty quickly after after the motor's insulation goes below the arcing voltages, it will get to a point where the insulation is below the bus voltage. Remember, this number that I have here represented as delta T. It's the difference in time between the moment when the insulation went below the arcing voltages and the time where the insulation finally failed. Remember that if the insulation is below the bus voltage, then you have a typical failure on the motor. Now, what you test for is, because when you're testing, what you want to do is you want to try and verify that the motor's insulation is above. You want to verify that the motor's insulation is above this point. As long as the motor's insulation is above this point, any point in the curve above this point, you can declare the motor to be good. But if the motor's insulation, when you are testing, is not good enough to withstand voltages up to 5 times per unit or thereabouts, depending on the voltage that you select, the standard that you're following, and the type of motor that you're testing, the criticality of your system and whatnot. But if your motor's insulation during your testing is not capable of withstanding this much voltage, then pretty quickly, even though you can probably put your motor back into service and it will probably work for a while, but if it cannot withstand this much voltage, it will probably fail very, very quickly. See, the form of the curve is such that it has a long time. See, the scale here is in years. A long time between the beginning and this point, but there is very little time between what we call the test fail zone and the motor fail zone. And the curve is built like that. This is a reliability curve, and Leslie will show you in her presentation that there are factors that can accelerate and can change the form of this curve. Here we are in what we call the good zone, and over here is non-linear but still good. And when you're testing and you're failing, which is here in this orange color, depending on where what your monitor is actually able, but anything above the red here is the test fail zone. And after you are in this test fail zone, you should not put your motor back into service. And this is what we are trying to find out with the tests that we are going to describe from now on. Now, the typical insulation tests used for electrical motors are insulation resistance test. This is the so-called Megger test. Then you have the high pot or high potential test. You have power factor and power factor T-pop, which are tests that I am not going to describe here. We may at some point do a webinar about it. There is the surge test, which is the last one that I'm going to talk about today. Partial discharge, which is something that will be discussed tomorrow. And then you have tests that are not insulation tests per se, but they are tools that you can use to somehow evaluate the quality of your insulation system by the effect of the insulation system in things like heat or generation of noise, etc. Now, when it comes to the insulation resistance test, we have polarization index and dielectric absorption ratio, as well as step voltage tests, which are, I should say, extensions of the insulation resistance test. And then when it comes to high potential test, we have DC tests, which are the ones that I am going to talk about today. We have AC tests, and then we have a very low frequency tests. I am not going to talk about AC tests today, but tomorrow, one of our panelists will talk about the very low frequency tests for rotating machines. So Here are the things that we are going to discuss from now on in this presentation. Now, the insulation resistance or Megger test, well, this is a test that's done using DC. Essentially, what you do is you inject a controlled voltage, you measure the current that circulates, and you calculate the resistance. Now, remember that the insulating material behaves as a capacitor when you apply voltage to it. You could apply either a DC or an AC voltage. If you're applying a DC voltage, then you're talking about the typical insulation resistance test. If you're applying AC voltage, then you will be talking about tests like power factor or dissipation factor, and that's a different test where you can measure things like the capacitance of the insulation, the dissipation factor, etc. Again, I'm not going to go in depth into AC testing. I'm simply going to discuss DC testing. Now, when it comes to the insulation, we have effects that, because it seems, I call this topic a deceptively simple one. It seems very simple, right? You apply voltage to an insulator and you get a current, you measure the current, divide the voltage by the current, and you have your resistance. It seems simple, but in actuality, there are different phenomena going on at the same time when you inject voltage into an insulator, especially when you inject a high voltage into a very thick insulator like that of a machine or any electrical apparatus for that matter. The first effect that we have are combined leakage and conductance, which are combined resistive effects. I should say that those are the ones that you want to measure when it comes to the insulation resistance. But like I said, the insulator behaves as a capacitance. So you have some current going into the insulation that is simply going to stay there in the form of a charge distribution. That's your capacitance right there. And then you have some other current. You can see it here on the under the absorbance current that's going into the insulation, but that's actually energy that's going to be spent changing the direction of the polarization plane of the molecules that form the insulation. Now, I'm not interested in this current or this current. I'm only interested in the leakage current, but all of those currents circulate into the insulation at the same time. So what I'm trying to say is that when you're doing insulation resistance tests, you have to give time for those processes to stabilize. You cannot wait forever. So you have to choose some time to perform that test, and that time, since the results are going to depend on how long do you wait, then what you have to do is you have to choose a standard time. Okay, so we'll talk about this a little bit later, but keep that in mind. Insulation resistance test is never an instantaneous test. You cannot just inject voltage, measure your current, and take your resistance right there. You have to wait some time for some of these processes, which have different time constants, to let's say dissipate or disappear or drop enough so that you are left with the current that you want to measure, which is this leakage current plus the conductance current of the material. Now, what can you do with the mega ohm test? Well, the first thing is you can determine if the motor has failed to ground. If you do an insulation test and you see that the test failed, then you're done. You don't have to do anything else. But if the test passes, then you don't really know if the motor is good. So the problem with insulation test is that it is a pass, no pass, fail. It can tell you if the motor failed, but it cannot tell you if the motor is good. One thing that is very important when we're doing insulation testing is trending. It's one of the most, I would say, powerful tools that we have. Here, we have two different insulation systems. One where the resistance is almost constant over time. This is the blue one, signaled here as motor one. And then we have motor two, which has values of insulation which are 2 to 3 times higher than the motor, the blue motor, but over time, the degradation of this system is such that this system is soon going to have values lower than this system. At some point, actually, in the motor number 2, at some point after 3 or 4 periods of measurement, someone should have said and should have stopped and said, okay, let's not measure this motor anymore. Let's do something to figure out why the insulation is dropping so fast. All right, but I guess that since the insulation was actually still above nominal, then no one was worried about this. Now, again, the mega ohm test cannot determine if a motor is good. It cannot find turn-to-turn faults. It cannot find an open phase, and it cannot find phase-to-phase faults. What are the voltages that you should use in an insulation resistance test? Well, there are tables in the standards. The numbers are fixed for insulation resistance. Again, what you should do is you should inject this much voltage. For example, if your motor is a motor rated for less than 1000 volts, you're supposed to test or do your insulation resistance test at 500 volts. If it is between 1000 and 2500, you're supposed to do it between these two values, etc. The standard tells you what. My recommendation is pick a voltage, use the same voltage all the time for a particular class of motors. The second thing, do the test for at least 1 minute so that you can get a result that's consistent over time. And always, always, always measure the temperature at which you took the resistance measurement and correct that resistance measurement to 40 degrees. Remember what I mentioned before, that for every 10-degree increase in the temperature, the resistance drops by half. Well, this is expressed in the fact that you are supposed to compare the values of resistance after you have corrected them to a standard value, 40 degrees C. And the standard tells you what are the recommended values of insulation resistance, the minimum recommended values of insulation resistance at 40 degrees C. You can find them in the standard. The takeaway here is that for most older windings, before 1970, the minimum in mega ohm is your kilovolts plus 1. That's a very old rule. A lot of people still use it out there. For most AC windings built after 1970, at least 100 mega ohms. Okay. Now, one thing, 100 mega ohms at 40 degree is 400 mega ohms at 20. So keep that in mind when you're doing your measurements, because a lot of times we're doing our measurements and the temperature of the winding is close to room temperature. We could be between 20 and 25. We get something higher than 100, but it may not be enough. And how do we know? Well, we have to correct the temperature. We have to correct the insulation to a temperature of 40 degrees C. And now this one down here, minimum of 5 for most machines with random wound stator coils, and below 1 kV. That's that. But you can find those numbers in the standards. Now, when it comes to polarization index and dielectric absorption ratio, what we are doing here is we are using the form of the total current, and we're using the fact that the total current should drop over time. As you can see here, it's high here, but then it drops over time, and it has the tendency to get as close to the conduction or leakage current as possible. And the difference is going to be the absorption current, since the capacitor has already charged here after, let's say, 0.7 seconds. This is just a typical example. Not it doesn't apply for every motor or insulation system out there. But the point is that if your current recovers, it means that you have a healthy insulation system. But if your current doesn't recover, you have an insulation system that's not as healthy. And why is the difference? Well, the problem is that if your current recovers, then that means that the main component of the drop in insulation resistance that happens at the beginning is the polarization component, and your actual leakage current is very low, which means that your resistance after some time is going to be very high. But if the main component of your current is actual leakage current, then your resistance measurements are not going to recover very well, and you're going to have this more flat or flatter curve. Now, polarization index is just now this is an actual example of a dielectric absorption ratio or polarization index graph, where we have the resistance here and the current down here. Typically, a lot of systems, instead of dividing the resistance when calculating the polarization index, they do so using currents. But the point is that the polarization index is, you only need two readings, one at 10 minutes, one at 1 minute, and you divide them both. See here, what I do is I take the measurement at 10, then I take the measurement at 1, divide them both. The greater the value, the better I am. The lower the value, the more damage I have in the insulation, as it is in this case, because you can see the value here at 10 is going to have a ratio much lower to the value of 1 when the curve is flatter. In curve number A, the difference is very big between the value at 10 and the value at 1, so the ratio is going to be higher for curve A. For the dielectric absorption ratio, what you do is, instead of dividing the 10 to the 1, then you divide the resistance at 3 minutes with the resistance at 30 seconds. Different materials will behave differently when it comes to the resistance. But the point is that whenever you have a contaminated material, there will be a sort of a flat response. Also, when the initial measurement of resistance is too high, then it may not make sense to calculate the polarization index, and you're supposed to take the dielectric absorption ratio instead. What can you find with these indices? Well, you can find deteriorated ground wall insulations, dry, rotted, hard ground wall insulation, contamination, moisture. The voltages are the same as those that we use for the insulation resistance tests. And here we have the minimum PI depending on the type of the insulation. And there is also a table for DA that you can find out there, even though if there is no standard, there are some manufacturers that recommend values of DA. Now, the step voltage test is used because typically when the insulation is good, you should have a linear relationship between the voltage and the current, meaning that as the voltage increases, the current should increase in the same amount, keeping the resistance constant. Remember that the resistance by Ohm's law is voltage divided by current. If we increase the voltage, the current should increase in the same amount in order to keep the resistance constant. But if after some point in the voltage increase that we are taking, the current increases more than what we increase the voltage, then that means that the resistance is dropping after some point. This means that there is what's called a voltage dependence on the resistance. And this could be an indication or early indication of partial discharge happening inside the material. In real life, this is what a graph of voltage versus current, the current is in red, would look like. Now, remember that initially we'd have this big spike in current because the capacitive current, whenever we are increasing the voltage, and then it will drop down to a lower point. What we're supposed to do is look for a linear relationship or a straight line drawn between the points at the end of each of the current measurements. And when we don't have that straight line, when there is an actual exponential behavior or some sort of increase, here at the end you can see it, then we are talking about a non-linear relationship between voltage and resistance, or what we call a voltage dependence on the resistance. The high potential test, what you do with the high potential test is you inject, and remember, all of these are DC tests. Again, I mentioned that you can do AC hypo tests, but the tests that we are discussing today are DC hypo tests, okay? So what you do for the hypo is you inject a high voltage, that is typically way higher than the nominal voltage of the winding. You hold it for 1 minute and you check whether the machine has been able to withstand that voltage or not. The temperature should not be greater than 40 degrees when you're doing that measurement. Remember that there is a relationship between the resistance and the temperature, and the resistance is going to drop the hotter you put the motor. So you don't want to heat the motor all the way to its normal operating temperature. You want to keep it at 40 degrees or below, and any measurements you do, you have to correct them to a base temperature of 40 degrees. You don't want to have a high ambient temperature. You want to reduce condensation as possible. The machine should be above ambient temperature so that there is no condensation in the machine. If you have humidity in the machine, that's going to affect this type of test dramatically. If you can, you should test each phase separately. It may or may not be practical. It depends on where you are in your testing, let's say, chain. And at the end, you're supposed to discharge the winding in time up to 4 times the if you injected the voltage for 1 minute, you're supposed to discharge for at least 4 times, sometimes that. Now, this not less than an hour. I guess it depends on how big is the motor that you're testing. And if you have machines that are 10,000 kVAs and 6,000 volts or higher, you're supposed to discharge them for a very long time, so that you don't have any effect of the dielectric discharge that can, dielectric memory, something that can, bring voltage back after you're done your testing. So you're supposed to do the discharge for a time that's at least 4 times the applied test potential. Now you can use these same methods for smaller equipment, and typically people they use the step test, and then at the end of the step test they do the hypo testing. Now, which voltages are you supposed to use? For DC, they tell you to use 1.7 times your AC test voltage, and that gives rise to tables out there that are, I should say, hard to follow. The minimum and maximum test voltages here, for example, the maximum test voltage should be 1.5 times 1.7. That's for new instruments, and then for new machines. And when the machine has been in service, then you're supposed to use a lower voltage. You're supposed to test somewhere between this point. The suggestion that we always do is that you test at twice the voltage plus 1,000. That's a very easy rule to use. It's very easy to remember. You don't have to, memorize 1.7 times 2 times plus whatever. Just twice plus 1,000 is a lot easier to use. IEEE and IEC, they have different tables, and it's sometimes it's hard to keep track of all the different voltages that you're supposed to use in that kind of testing. Now, for surge testing, here, this is the last test that we're going to discuss today. Surge testing is the type of test that you do to check the turn-to-turn insulation on the machine. Now, the test circuit used is here. The coil will represent the machine that we are testing. This capacitor or discharge capacitor is the capacitor whose charge you would be discharging into the coil, and then when that charge is discharged into the coil, then a resonant circuit is formed here with the ring capacitor, and then we capture that the waveform that results from that. If we look here, what we are capturing is the voltage of the coil. Now that waveform will have a frequency. This is an resistive inductive capacitive circuit, an RLC circuit, and the response of an RLC circuit will have a frequency that has this form. Now, remember that the inductance in coils have an equation that's roughly, let's say, proportional to the square of the number of turns in the coil. So what we're doing here is we are injecting a voltage into the coil and creating a resonant circuit. And as we increase the voltage, there will be a point where some turns of this coil, I mean, if there is a fault in the coil, some turns of this coil will be shorted. When you have shorted turns, then the effective number of turns in that coil is going to drop, effectively dropping the inductance. And when the inductance drops, see how we have an inverse relationship between the frequency and the inductance. So as the inductance drops, the frequency is going to increase. And we can measure that. We can determine how much has that waveform changed when one or more of those turns were shorted by the effect of the increase in voltage that we are applying to the coil. So what we're doing essentially is we are injecting a voltage here, a small voltage, then we are injecting then this small voltage means that I have a turn-to-turn voltage represented here by the red line. And then this will be my delta in the voltage. As I start increasing the voltage, there will be a time where perhaps I will have an increase in the turn-to-turn voltage that's going to be high enough to short those turns. Now, that the shorting of those turns will only happen if you have a problem that's brewing in the machine, if you have a weakness in the insulation that you cannot see by any other means. None of the other DC tests that we discussed is able to find the type of fault that we can find during surge testing. So in the end, what can we find with surge testing? We can find weak insulation, turn to turn, phase to phase, coil to coil, any problem in the insulation. Now, I forgot to mention one thing. See how the distribution of voltage is non-linear across the winding. This would be, T1 would be the side of the terminal that's closer to where we are injecting the voltage. And T4 is the side of the terminal closer to ground or closer to the neutral, depending on what we have, how we have connected the system here. So the early turns or the turns that are closer to the lead are going to get the maximum amount of voltage. And this simulates what happens in the machine when the machine sees voltage spikes that are generated at the leads, which is what happens when we have either a motor start or when we have the machine operating using variable frequency drives or commutated sources. So this can find weak insulation in, like I said, turn to turn, phase to phase, coil to coil. In the shop, when we are testing, remember to remove the rotor. Now here we can find a weak insulation, we can find reversed coils, we can find turn to turn shorts, unbalance, anything that affects the inductance of the winding, we can find with this test. Now remember that the inductance can be affected by the by mu. It can be affected by the number of turns. It can be affected by the area of the coil. It can be affected by the length of the coil. Any of these parameters that changes, and here we have the permittivity of vacuum represented in this equation, but a typical equation with magnetic material will have the permittivity of the magnetic material multiplied here. So the properties of the magnetic material are also represented in the inductance, and those properties of the magnetic material can change if we have, for example, shorted laminations, if we have a different size copper wire, also if we have a reversed coil, then we may have less inductance that we should have had. So anything that affects the inductance of the coils can affect the results of the surge test, and can therefore be detected using this type of tests. So in the field, we compare poles to poles error area ratio. In the motor shop, we compare waveform. We can compare line to line error area ratio because we don't have the rotor inside the machine typically when we are in the shop. Now, what is the error area ratio? Well, that's the way we use to compare two consecutive waveforms. We simply, well, not simply, but what we do is we measure the area of one waveform, the area under the curve, and then we measure the area of the next. And we use a mathematical procedure to compare them. If their difference is bigger than a specified number, then we declare a fault in the test. Now, whether there is a fault or not depends on the condition, so that this takes a little bit of experience on the part of the person who is doing the testing. We have line to line error area ratio, which is when I'm testing, let's say on line A, and then I do my test on line B. Supposedly, if I have the same inductance on both, then I should have identical waveforms. If I have the rotor outside of the machine, the difference should be very low. If the rotor is inside of the machine, the difference is going to be bigger because the position of the rotor inside the machine changes the inductance of each of the phases. So that is typically a cause of confusion when we are doing this type of test. This is an example of the influence of the rotor. So again, when we are testing in the field, we are supposed to use a pulse to pulse EAR, because pulse to pulse compares the winding against itself. But when you're testing in the motor shop, where you can remove the rotor, you can use both the pulse to pulse, comparing the winding versus itself, but you can use the line to line comparison, because since the rotor is not in, then we have equivalent inductances between the three phases. This here is an example of a failure. Here we have two phases that passed the test at 9760. This was a 4160 volt motor. So I was testing it at twice plus 1000, 9,000 volts. I actually raised the voltage a little bit more. And then this phase, lead number one, failed at 4,000 volts. You can see here the difference. These two were very similar. Now, they were not perfectly aligned because the rotor was in the machine. Actually, everything was in the machine. The machine was in the factory. But the last one actually failed way below the other two. There was a lot of argument that day. Hey, is the problem with the leads? We changed the leads, we swapped, but the problem was always on the same lead. This is just a blowout of the same failure. Now, you can have different, let's say, waveforms that you will see. Sometimes you will see something like this. Now, always remember the equation. I should have put it here, but I didn't. The equation of the frequency. There are parameters in the equation of the frequency that are the inductance, but there's also the resistance. Sometimes when you have a resistance that's too big, then you will have a frequency that's very low. And when the frequency is very low, then you have an elongation of this waveform, because remember that this is time here, and the frequency and time, they have an inverse relationship. So the smaller or the shorter the frequency, the longer the time, and the higher the frequency, the shorter the time. So this red one has a higher frequency, the yellow one has a lower frequency. This could be because I have a high resistance. In some cases, it will be so high that it's almost declared as an open, and you will see the effect on the waveform right there. Now, this is pulse to pulse EAR. This is how a error area ratio graph is supposed to look like, where I have a maximum pulse to pulse of 1.9% between leads. I mean, inside the lead. Remember, this is pulse to pulse. And this one here is where after sometime we had high pulse-to-pulse EARs. Lead 1 tested at 5.5, but then leads 2 and 3 had very high pulse-to-pulse error area ratio. Now, when it comes to the voltage that we're supposed to use, we recommend that we use the same voltage twice plus 1000. But here is the you can if you do the math and you put the twice plus 1000 here, you'll see that it's actually similar to the voltages recommended by IEEE. It's somewhere in between. But the IEC recommends voltages much higher, which I guess is an answer to the question that do these tests damage the motor? Well, the way we do it here in North America, they don't. They allow us to find problems. What I'm trying to say is that not even the way they do it in the IEC, where they recommend much higher voltages, doesn't damage the motor. Now, summary, what we have touched in the presentation are the typical failure modes and the failure mechanisms of electric motors. Then we talked about the insulation resistance test, polarization index, and the electric absorption ratio, step voltage, high pot, and surge. And then we have several products here that I wanted to share with you that go for that are used to test electrical motors. These are testers or products that are designed specifically to test motors. Here we have the MTR 105, which is a handheld device that allows us to do Megger tests, and then it also allows us to do winding resistance, rotation, allows us to do polarization index and electric absorption ratio. It's a fantastic tool in the hands of technicians. It has an input for a thermometer. You can measure the temperature. It has alarms. It can download the results to a USB, and then you can import them into a PC with PowerDB and use the results right there. It has everything but a source tester. Now, AWA and DX unit, they are, I would say, the workhorses when it comes to testing motors out there. The AWA is automated. The DX is a manual unit. They have similar voltage capabilities and also similar features when it comes to the amount of things that they can do. Difference being that the DX can measure the impedance and inductance, and it can do PD. The rest of it is they are very similar. The AWA4 is a very nice unit. A lot of people love it because of the automation and the fact that you can just program your test there, keep your trending databases. It has a Windows operating system inside, so it's a fantastic tool. And then we have the power packs that can be used to increase the size of the motors that we can test, not just in the voltage, but also in the size in terms of power of the motors and generators that we can test. These units have to be controlled using either an AWA4, a DX, or a power pack controller. And there are other instruments that we have that can be used. Remember, all the tests that we talked about today were insulation tests. The Delta 4000 is an AC insulation tester that can do power factor, everything related to power factor, and that goes all the way to 12 kilovolts. It can measure dissipation factor, it can do power factor T-pop, capacitance and inductance, and it can do narrowband DFR. And a very unique thing is that it can do individual temperature correction by doing a narrowband DFR. That's a little bit, there's a little bit of theory behind that, so we don't have a lot of time right now. The S1, it's a Megger tester, one of our most popular units. It goes from 5 to 15 kV. It can measure off to up to 10 teraohms. It can do automatic tests. You can connect it to a computer and do insulation resistance over time and get the results into a computer. It's a small, powerful DC tester. There's a whole line of them. Then we have the Trax, which is our, I don't like to say this, but it is our Swiss Army knife. It can be used to test almost anything out there. Like the Delta, it has a 12 kV AC capability. There are models from 200 to or 800 amps, and it can do everything. It can do power factor T-pop, I mean, any measurement out there, and it has mathematical functions that you can do on the inputs of the different voltmeters and ammeters that it has, and it can measure phase, frequency, and magnitude in all of those ammeters and voltmeters. So you can basically design a measurement, do it with the tracks, even if the app is not right there. And then for resistance, which is something that we didn't talk about today, but I mentioned at the beginning, it's one of the tests that you should do. Then we have the low resistance ohm meters here, the DLRO. This presentation will be available to you, so you can take it later with you. And at the end, we are running a promotion. Michael, I guess this is your time, where I just wanted to mention that you can save 10%. I guess you mentioned that a little bit at the beginning on all the Megger Baker equipment that we talked today. And there will be details on the email that will come out later. You just have to use the promo code motor. All right.
Yep. We'll try and have all that information on the follow-up email. I'm going to aim to have out tomorrow morning before our day 2 of this same seminar. But moving right along, we're going to jump into our Q&A segment. We're going to try and answer as many of your questions as we can before we jump into our next presentation by Leslie Reed. If you have any questions, please enter them now into the Q&A section on our GoToWebinar control panel. But jumping right in, my first question I'm going to direct to Leslie Reed. Leslie, what is the normal operating temperature of a motor under normal condition? Is 80 degrees Celsius okay on some parts?
So it's a good question and difficult to answer with one answer. So it's one of those depends. So it depends on, first of all, the ambient temperature which that motor is operating in. So ambient is stamped on the nameplate of a motor. So that is the manufacturer's design where they were trying to hit, most often it's 40 degrees C. So the insulation class that's put into a motor has to do with at what temperature that motor is rated at. And ambient goes in part of that. So it's going to take the ambient temperature plus whatever temperature rise that motor has up to full load. And then they basically pick the wire that's going to give them that kind of time on the motor. So the rule of thumb of 10 degrees for every 10 degrees C rise in temperature, the rate at which the insulation degrades accelerates, basically doubles. So each 10 degrees rise in temperature is having the life of that insulation. So that is any 10 degrees rise. That's not just 10 degrees rise above full load. It's any 10 degrees rise that affects that temperature, or affects the insulation, the life of that insulation. So 80 degrees Celsius may be okay for that motor if it's in a ambient temperature of what that motor was designed for. However, if my ambient temperature is at 60 degrees C, then I may be overheating that motor just because it starts out so high. So that in that case, you'd want to pick a motor that had a 60 degree ambient temperature rating on it. So hopefully that kind of answers the question there. If that question is in response to the 10 degrees rise, know that any 10 degrees rise in temperature is either is having the life of that insulation. That's what we should be concerned about there. Michael,
Right,
next
Leslie.
question.
Next question is also to you. Should the winding resistance condition be determined first before proceeding to other electrical tests?
So Abel actually was trying to focus mostly on the tests that directly evaluate insulation life. So, and I know our manual does have in it, and the AWA actually, that's the first test you'll encounter is the resistance test. So what does the resistance test do for us? So again, it's part of the low voltage testing group for static testing. We have a resistance test and the MEG test, the PIDA are all low voltage tests, considered low voltage because they are done at or near nameplate voltage. And it is good to do that test first. It kind of gives you a look at connections of that system. So if you're testing from switchgear, you're going to lift the leads from the power source there and test at that point. So now we're testing the cable all the way through the junction box and those connections to the motor. So resistance testing, then we're looking at balanced resistance there of the three phases, as long as they're very balanced. By balanced, I mean within usually typically 3 to 5%. Then we have a fairly good system there. But we have imbalance in our resistance there, then that's going to possibly affect our other tests. We want to know about those connections and make sure we may suspect there's something in that junction box that's causing an imbalance in the resistance. So typically it is the first test that is performed in this series of tests.
Great, thanks, Leslie. Next over to Abel. Abel, why does the presence of the rotor inside the machine affect the result of the surge tests? What can be done about that?
Well, I don't know. Well, I had the let's say the equation that everything you do in surge, you can refer back to that equation where I presented the frequency of the resulting waveform. And remember that in that equation we have that the frequency has an inverse relationship with the inductance. So any change in the inductance will change the frequency of the resulting waveform. Now, in a motor, in a three-phase motor, when you're testing, you will be testing line 1, then line 2, then line 3, which are phases A, B, and C, or depending on where you are in the world, how you represent those phases. But they will be phases 1, 2, and 3 of the motor. For each of those tests, you have a different circuit inside of the machine, but the resulting inductance should be very similar to each other. The problem is that when you have the rotor inside of the machine, the position of the rotor will change the resulting inductance, because that's what machines are for, right? The change of inductance of the machine makes the machine move, basically. Right? I mean, I'm not going to go into the principle of operation of the electric machine, but you can think of the machine as a changing inductance all the time as the rotor moves across the stator or around, so and that happens with a frequency that is also related to the number of poles of the machine. So if you measure the inductance of one line, let's say line number A connected with line numbers 2 and 3, or A, B, and C connected to ground, and you move the rotor in a circle around the 360 degrees, you will see a sinusoidal pattern emerge that has a frequency that's related to the number of poles of the machine, and it's going to be the frequency is going to be higher for a larger number of poles. So you have every 360 electrical degrees on that motion, you will have that sinusoidal movement of the magnitude of the inductance. It never goes to 0, but it does have a maximum and a minimum, and it has an average value around which it moves, right? So the point is that if you do that for phase A, then for phases B and C, you will probably have, or you'll most surely have, a different value of the inductance. The point is that if you do a surge test for line A and you're trying to compare, and then you do the same surge test for line B and you try to compare both waveforms, the difference between them cannot always be attributed to an actual short. Sometimes the difference between them can be attributed to the normal change of inductance or the normal difference of inductance because of the position of the rotor inside the machine. And that's why when you are doing tests with the rotor inside, you're not supposed to compare line-to-line waveforms. You're only supposed to compare pulse to pulse, because pulse to pulse, what you're doing is you're comparing against something that has a fixed inductance, which is the machine. I'm sorry, the winding that you're testing. Pulse to pulse simply is I'm testing winding A and I'm increasing the voltage a little bit by bit. and I compare this pulse to the next pulse. And then after some times, when I fix the voltage, I can compare one pulse against the next without any change in the voltage. So that's why you cannot rely on line-to-line comparisons when you have the rotor inside the machine, and that's how I would say the inductance is affected by the presence of the rotor inside the machine.
Thanks, Abel. And since we're running a little bit behind on time, we have time for one last question. And is it possible to do surge tests at the same time as checking the partial discharge? Additionally, for a 6.6 kV line-to-line motor voltage, what equipment do you recommend for me?
Okay, let me answer. Okay, first, yes, it is possible to do surge and check for partial discharge. Partial discharge occurs when you have changing conditions of the voltage. You don't typically see partial discharge when you have DC. You see partial discharge when you have a voltage that's rising or dropping, and you see the partial discharge start or finish. And that's why you have the partial discharge inception and then the partial discharge extinction voltage. So you can check partial discharge with a 60 hertz waveform, or you can check partial discharge with a surge waveform like the one we were showing there. So the answer to the first question is yes, because that's what the two-part question. Now, for a 6.6 kV line-to-line motor voltage, well, I would recommend that the first thing you do is you cannot simply rely on the voltage, because the size of the motor, how much power does that motor or is that motor capable of putting out, will determine how big the frame of the motor is. And depending on how big that frame is, that will tell you how big the capacitor that the motor forms, or that the motor insulation forms, is. So my point is that in order for me to be able to tell you what machine you need to use for a particular application, the voltage is not enough. Now, if we were going, because of course I would need to see the power, and then I may need to tell you that our machine, the DAS, I don't know, the 14 kV that you need is not enough. Maybe we need to go higher in voltage, because with machines that go higher in voltage are also capable of testing machines that have higher power or higher or larger frames, you know, or bigger capacitances. So, but if you were going to go only on voltage, I would say that you do the 2 plus 1000. So you do 12, 13, 14, 15 kV machine should be able to test this motor, with the, you know, a question over being whether that machine is enough when it comes to capacity to test the 15 or to give you 15 kVs with the frame that you have. So in order for me to answer that question properly, I would need to know also the power that that motor has. All right.
We do have a follow-up question since you need the power. The follow-up with that is 2200 horsepower fan with 50 hertz.
Then more likely our 15 kV AWA or DX can test that machine. 2200 horsepower? Is that what it says?
Yes.
Okay. Yes, our DX 15 would do it.
All right, excellent.
Yep.
So in the interest of time, I'm going to move us into our second presentation with Leslie. Leslie, are you ready to receive presenter control?
I believe so.
All right, here we are. You should have a prompt up on your screen. Beautiful.
Yes, the prompt.
All right.
And
we'll just jump in.
Should be good.
Yep.
Looks good,
We're
Michael?
green for go. Yep.
All right. Well, everybody might need to stand up and stretch a little bit. I had to. Get a little sore sitting there. We're going to switch gears just a little bit to a different technology, but still has very much connections to what Abel has described to you. we'll take a look at dynamic machine monitoring and how it identifies factors that lead to electric motor failure. So our key takeaways today here is understand the factors that lead to insulation degradation, and Abel had a like one slide there where he talked through several factors that lead insulation to degrade. We're going to look at some more of those factors that specific to the dynamic testing and what it looks at, how dynamic machine monitoring can identify factors that lead to insulation degradation. So we'll list those factors and then show how dynamic monitoring here can identify those factors that lead to insulation degradation. And then we're going to distinguish the complementary aspect between static and dynamic testing, and how they could work, how they do work hand in hand to help you with reliability of your motors. First of all, we'll look at the insulation failure mechanisms. And again, I know Abel has gone over this. We've looked at this life curve, and now you know kind of what those numbers mean at the upper left. Our capacity of the motor there of copper to ground, the ground wall insulation at being very high for, this is for a 460 volt motor, and copper to copper, we've got 16,000 volts AC there. So we've seen this graph and wondering why it's shaped that way and what's causing that insulation to degrade over time. So the dielectric strength of that insulation over time drops, and as it drops, if it drops below that operating voltage or bus voltage, that's when we have that catastrophic failure. So dynamic testing will help us identify those factors. And one of those factors, the biggest one, and this one is the one that Abel had on his screen there, is that for every 10 degrees rise in temperature, that insulation is going to degrade. And the rate at which it degrades is it doubles, or it halves the life of that insulation. So here, if we had a insulation class F, which is rated at 155 degrees C, so even at full load at 155 degrees C, it would be expected to last 20,000 hours. But if we increase that temperature just by 10 degrees, we're now at half the time, half the life of that motor. So heat that causes, heat causes insulation to degrade over time, and there's a lot of things that cause heat in the motor. So we've looked at the doubling rule there. We've looked at the contamination. We've looked at mechanical movement and the overvoltage spikes that caused by the switching surges there, breaker opening and closing operations, and VFDs, variable frequency drive or variable speed drives, cause those overvoltage spikes. Let's go ahead and take a look at some more factors here, as our power quality and how that plays into the ability for that motor to do its job. So overvoltage, undervoltage, both of those situations cause heat in a motor. So if we're over voltage, so we're supplying higher voltage to that motor than what it's rated at, our strength of our magnetic field, which is directly related to our voltage squared. So we have a strong magnetic field in that motor, which means that it actually has to draw less current to do the same amount of torque, to produce the same amount of torque. So we would think that because it's drawing less current, that motor would be running cooler, more efficient, which is true, but of the amount of time that it spends in that overvoltage situation, we can saturate the iron core and cause hysteresis losses and eddy currents to be in that iron core. So it's going to heat due to increased currents in the core, which then in turn heat the windings. Undervoltage, I think we're really easy to understand why undervoltage would cause heating in the motor. Undervoltage meaning that we're supplying less voltage than that motor was designed to power. So the motor is going to raise the current. It's going to draw more current in order to produce the same amount of torque if it had the proper voltage, and that's going to cause it to heat very rapidly. Voltage imbalance. So this is where we have a three-phase voltage being supplied to the motor. And three-phase power should be equal for each of the three phases, should be the same. And if we have a phase that has either higher or lower voltage than the other two legs, it's going to cause heating in the motor. Distortion, so if my power is distorted, whether it's harmonic or non-harmonic in nature, the distortion of that perfect sine wave that we're trying to feed to the motor of our power, if it's less than perfect because of other frequencies that are found on the bus, causes, again, extra currents, extra circulating currents in the wrong direction, causing the motor to have to draw more current in order to produce the same amount of torque. So both of these, all of these items here in the power quality can cause heat in our motor. Corona, partial discharge, again, is something that causes heat in the motor. Partial discharge is really the insulation that has a void in the insulation, and it's arcing within that void. And that process of when it arcs actually produces a gas. It's ozone, it's caustic to insulation and directly attacks insulation. And corona is the visible part of that. And it's not something you want in your motors, again, destroying insulation. Other factors here are load related. So overloading of the motor, as we put more load onto a squirrel cage induction motor, the rotor slows. It slows down, drawing more current, so we get more induced voltage, more current draw, we get more torque production. So we put more load onto that motor, it's going to draw more current in order to meet the demand of that load. Drawing more current has the effect, of course, of producing a lot of heat in the motor. Misapplication of the motor. So again, we want the right sized horsepower motor in that application, but not only just the right size horsepower, but we also want to know that its startup characteristics are complementary to the load that it's driving. So if the startup characteristic of that load requires high torque at startup, but our motor wasn't designed to give that, then that motor is going to overheat and be destroyed. It will not last that long in that position, in that application. So again, NEMA design is stamped on the nameplate of most motors. B design motors are typically, is the most typical motor out there. It's also the lowest starting torque. So if again, when replacing a motor, we look at horsepower, frame size, RPM, voltage, but we should also look at its design, its NEMA design as to its startup torque characteristics, so that it would match the application. If not, we will be burning that motor up more quickly. Frequent starts and stops. So not only is the starting process, as Abel described to you, hard on a motor, it's probably the worst thing you do to your motor on purpose is to start it, but if to have back-to-back startups are even harder, because as we start that motor, we get that rapid heating. The motor heats up because of that inrush current. And if we shut the motor down and start it again, right back to that, our motor's already hot, and it's going to get even hotter that second start. So we have to put protection systems around our motors to protect them against themselves, basically, and to protect them against operators who want to perhaps unjam a log or of a conveyor belt and bump the motor a couple of times. So in doing that, it's causing quite a bit of heat in that motor, and heat destroys insulation. Startups and shutdowns, we've talked about being very hard and causing a lot of heat in the motor there. There's the list. Other things that cause, factors that cause insulation to degrade over time. Some of them are not so much time related, but come from the manufacturer that way. Voids, nicks, inconsistency in the manufacturing process, mechanical weakness. And a lot of this can be checked out when you first get that motor and you receive it in either from your motor shop or from the manufacturer, is to do a static test on that motor and make sure that that something didn't damage in the process of transportation. You may have the best shop in the world, but in transportation, damage was done, and you received then a less than ideal motor. So all these factors cause that cause failures in motor. Again, with manufacturing faults, improper lead labels kind of tend to misguide us sometimes when we're hooking that motor up. So again, we want to visit this insulation life curve. So we have motor A here, and its dielectric strength. And we also, what happens here with static testing is that static testing helps us identify where on that insulation system the motor is, where that insulation system is on that curve. So we're going to take and do the static tests, the resistance, insulation resistance test, the high pot, PIDA, surge testing. All that helps us to directly evaluate that insulation system and would place it on this curve. If we're in that linear zone that Abel talked about, we'd be up here. Test Bell zone would be where we see these orange dots here. And then, of course, motor fail zone is where we're not doing the testing and the motor fails in service, where the dielectric strength has fallen below bus voltage. So we may have also motor, a different motor, or we may have our motor A here that has a voltage imbalance. That's going to shorten the curve that that motor is on. And dynamic motor monitoring helps us identify which curve it's on. So if it could be that we have voltage imbalance or broken rotor bars, it's going to shorten the life of that motor. If we're overloading the motor, then we're shortening the life of that motor. So if dynamic motoring helps us identify which of these curves it's on, and so if we're failing tests in dynamic, we're getting warnings and cautions about overloading, then we know that that motor is on a shortened curve, and that at that point we can stop overloading it, putting it on back at a normal load, and then we've then short circuited this. We've actually moved that motor back over to its intended path. Other things, harmonics, low voltage, all those things are things that the dynamic testing will identify. So dynamic monitoring helps us to define which curve. So if we have two motors, A and B's on a shorter curve, what's causing that motor to be on a shorter curve? Those factors are what dynamic testing is going after. So what is dynamic electric motor monitoring? We tend to use the word, instead of testing here, is that we're going to monitor it, because we're not injecting anything into the system here. We're kind of silent watchers of what's going on with this motor. And even the words motor here is kind of not an adequate definition here. It's really a complete system analysis. So dynamic electric motor monitoring evaluates each component of the electrical mechanical system and identifies the environmental factors that will accelerate insulation degradation. Whereas static testing then directly evaluates that insulation integrity, identifies insulation weakness, and predicts electrical failure. So those two are separated out. One's looking at the environment that that motor is living in, and the other one is directly evaluating that insulation. So let's take a look at each of those components there. Power supply. So we're going to get information about our power supply, our motor, and the load. So the power supply, what is its purpose? Its purpose is to provide electrical power for motor operation at a specific frequency and voltage. So in the United States, North America, we do 60 hertz for our supplied voltage. Europe, it's 50 hertz. If we're on a variable frequency drive, then it could be anything. So power supplies can be either fixed or variable. However, most motors in the industry today are three-phase, need that three-phase power source. And the bottom line here, why we're concerned about power, is because power quality has a direct impact on the motor's ability to produce torque in an efficient manner. So we have a motor to do some kind of work. We have to supply power to that. And the motor takes that power, whatever we give it, to try to do whatever we're asking of that motor. So if our power supply is bad or weak, then we're going to have extra current being drawn for that motor, which is causing heat in the motor, and is going to cause that rate of insulation to degrade, rate to be faster of the insulation. So we are concerned about what kind of power we're giving this motor. The motor, its purpose, it's the guy in the middle. It's to convert that electrical energy into mechanical energy through the use of magnetic field generation, induction, and field interaction. The motor sits at the point of electromagnetic conversion from the electrical into the mechanical in the form of torque. So while the motor produces the torque, it is the power supply and the load which define how much torque will be requested of the motor to deliver. So the motor sits in the middle and just basically does what it's told. The load is going to request a certain amount of torque, and the power supply gives it a certain amount of power, and it's up to the motor to make it work. And basically, with the motor, we are going to use that motor as our sensor. So for dynamic testing, we're going to hook up to the three-phase power, the 3 voltages, and we're going to have current transformers. We're going to clip onto our leads to measure the current. So we're going to take voltage and current, and through that, we're going to be able to determine what our power quality is, what our load's doing, and its reaction, the motor's reaction to that. So we're using the motor as a sensor. Now, unlike the vibration world, who has highly calibrated sensors, accelerometers, they're calibrated. Here, our motor is just whatever it happens to be, right? It's not a same for each of our tests. So we kind of have to take in consideration what is particular to that motor. The load's purpose here is to harness the mechanical power supplied by the motor into useful work. And again, the load varies a bit. Pumps, fans, compressors, gearboxes, conveyors, crushers, mills are just a few. Bet you guys could come up with a few too. Each load carries with it a unique torque demand. Not only the amount of torque required by the load, but also how it's required, the nature of it. The torque demanded by a reciprocating compressor is much different than that of a centrifugal pump or a rock crusher. And the torque demand there was something we're going to give you with the EXP or dynamics testing in the form of a torque ripple or instantaneous torque. And that draws us a picture of what that motor is seeing through the air gap of that load. So again, here's our electromechanical system. We've got our power supply, our motor, and our load. The power supply supplies that power at a certain frequency. And as we supply the voltage to that motor at a certain frequency, an electromagnetic field is created in the stator of that motor, and it's going to spin at a certain speed. And the speed at which it spins at depends upon the frequency of frequency of the supplied voltage and the number of poles of that motor. That will give us our synchronous speed. Synchronous speed is the speed of the spinning field in the stator. And because we have a rotor installed, that rotor is constructed into bars. It has shorted bars, basically a ring that looks similar to a squirrel cage or a hamster cage. You might know a hamster cage. I've never seen a squirrel cage. And those bars are shorted. So we put that inside that spinning electromagnetic field. We're going to induce a voltage into the rotor. We'll have a current flow due to the shorted bars, and it chases that electromagnetic field. And the difference between the spinning of that rotor and the spinning of the electromagnetic field in the stator, that difference is slip. The slip is what's going to give us that torque production. So the difference between the spinning field, electromagnetic field, and the spinning rotor is slip. Slip is directly related to torque. So if we put more load on this motor, it's going to slow the rotor down, draw more current, producing more torque. So as it produces more torque, or the request for more torque comes in, the motor goes back to the power supply. The power gives it voltage. It draws the current then in order to produce that torque that is requested by the load. So these relationships between the power supply, the motor, and the load are what dynamic monitoring explores and gives us information about. So here's the definition. It is the ability to find power conditions, motor, and load-related issues while the motor is running under normal conditions. By measuring and analyzing and trending the currents and voltages of the motor load system, typically we do this at the switchgear or the MCC. What we get from that, the analysis, helps us actually look at root cause of the power quality mode load issues. So it does well at finding root causes. With the static testing, we can pull a motor out, directly evaluate the insulation. If we have a failure there, whether it's to ground or turn to turn, we know that the motor is bad, but we don't know why. Dynamic testing kind of gives us the why. It can help us find the root cause of problems. It helps us define mechanical issues such as bearing problems, rotor bar issues, cavitation, eccentricity, power quality issues including out of spec levels, imbalances, transients, and distortion. And then of course, it also helps us define the motor's operational environment. How is that motor reacting to what we're requesting of it by the load, by the power that we're giving it in its situation? We're getting its operational environment. So we have two different lines. We'll look a little bit at product here. 2 lines for dynamic testing. We'll see on the left here is the NetEP. The NetEP is an online instrument, so it would be permanently installed, and then you can run cabling to it to continuously monitor up to 32 motors across 7 different voltage buses. The EXP4000 is our portable offering. So this is an instrument that you would pick up and take around to the motors in a portable way. And both of them will identify power quality monitoring. So improper tap settings, poor distribution, overloading, missed and open power factor correction capacitors, voltage surges and sags, or information that it can give you. Motor performance monitoring would identify, again, overloading. So again, heat in the motor, deterioration from heat-related issues. So overloading is going to cause those heat-related issues. Motor efficiency, speed, load percent. Current modifying, looking at just the current aspect there. We got overloading, high resistive connections, misconnections. Iron saturation can cause current issues. Improperly wound motors, saturation problems, broken rotor bars, eccentricity, all can be seen in the current spectrum. Torque is another parameter that we look at here with both instruments. So mechanical issues, transient overload, mechanical imbalances can be seen in torque. Bearing problems can be seen in torque. Cavitation, worn impellers can all be seen in torque. So the EXP becomes almost this well, the inventor of it, Ernesto Wiedenberg, he called it the judge. And I know that you guys have experienced it where the electrical guys and the mechanical guys don't always agree. Electrical guys saying it's the pump, mechanical guys saying, nope, it's got to be the motor. If you put the EXP or dynamic testing on to that motor, a lot of times it acts as a judge. So if you see issues in torque, that's mechanical. It's definitively mechanical issue. There's nothing wrong with the motor per se. It happens to be the mechanical side that's having difficulty there. So benefits of dynamic testing: reduced unscheduled downtime, helps determine the root cause of analysis, helps separate mechanical and electrical issues. Again, reduce that costly troubleshooting time, provides early warning. You can see if you're starting to get issues in let's say rotor bar issues, it will show up as an early warning. You get warned, hey, I'm overloading this motor, meaning I'm causing heat in that motor. Again, opportunity to take a look at what's going on with that motor. Provide support for other technologies. It's used hand in hand with vibration to help determine what the issue is with this system. Again, saving money, motor quality assurance. You get that new motor in, put it into the application, get a baseline at that point. Again, use it to extend the motor's life. We've discovered this motor was on a different curve, and we've corrected those issues. And so now we're going to extend that life because we've corrected the issue behind what was causing issues there. So we're going to ask some questions, and how we're going to find the answers to them. So, is the motor operating properly? So this word "proper" is important here because not every motor operates the same. So this motor in this application, is it operating properly? What's proper for that load? What should it look like? If I have a rock crusher, its loading, its torque ripple, its instantaneous torque, what's coming through that air gap, is going to be very different than that of a smooth running pump. As a rock crusher, as it hits rock and crushes it, you're going to have a lot of swing in that torque, whereas with a smooth running pump, it'd be very smooth. And if my pump looked like my rock crusher, then I'd be upset. Then something's going on with that pump, more than likely cavitation. If my rock crusher looked like the smooth pump, then there's an issue with the rock crusher. Is it doing anything? Is it turned on? So what's proper for that load? What's proper for that motor? How is that motor reacting to the load? And that's what we're seeing through the air gap. What is the condition of the power? Are we giving that motor the best chance to take care of the load that's requesting torque from it? So how we're going to find those answers, we're going to observe the voltage and current supplying that motor. We actually obtain speed. We estimate speed, which helps us then determine the torque of that motor. We analyze that data and we trend it routinely to find those answers. So the dynamic testing parameters here that we want to look at would be voltage. It's the only one that has a high and low, and it can be imbalanced and distorted. So all those contribute to heat and degradation of the insulation. Current can be high. Again, it directly affects the heat in the motor. It can be imbalanced. The other thing about current we look at is rotor bar sideband is in the current spectrum, which would indicate current oscillations associated with rotor bar asymmetries, such as broken bars. Load can be high. Again, high overloading is going to cause the motor to draw more current and increasing the heat on that system. It also adds mechanical stress to the system, not just electrical stress. Torque can be high. It can be have oscillations, can have high spectrum peaks. So if the torque is just high, that's putting stress on the shaft line components. It may be due to overloading. It may be other things that are going on there. Oscillation is a process variables or mechanical defects that are causing the oscillation. If the motor's on a VFD, those oscillations in current, it could be the process variables of that VFD. High spectrum peaks at specific frequencies of interest. So here, if we have high spectrum peaks in the torque spectrum that have that correspond to the frequency at which your bearings, ball pass frequency, or the inner and outer race, the ball spin frequency. If we have a peak that comes up, that's an indication of a mechanical issue with that particular motor. Startup analysis is another section that we can actually capture data while the motor starts up. We capture voltage and current. So the voltage, if we can see how long, how much the voltage dips as we turn this motor on and pull, how stiff that bus is. How long does it stay in that inrush current? So we can determine how high the amplitude and how long the duration of that current during startup, and that can indicate a variety of issues. Why is my motor staying longer in that startup period? Why is it taking so long to get up to speed? We can also note the torque that's required by that application. So we'll basically draw you the startup torque characteristics of that motor. And so you can determine whether or not you've got the right type of motor, NEMA design, of motor in that application. So these are all the parameters that we look at in dynamic monitoring. So let's look at some specifically here. So under overvoltage, motors are designed to operate within 10% of rated voltage. The voltage supply deviation really should be less than 2%. When operating under or over voltage, a motor's performance, its efficiency, and power factor change. Voltage issues are usually caused by poorly performing or improperly adjusted transformers, undersized conductors, poor connections, low power factor sources in the distribution system. So low voltage cause higher currents, higher heat. It's pretty direct relationship there. We're going to have more current flowing through the windings with a lower voltage. This is going to create more heat and burn up through the insulation fairly quickly. High voltage, we're going to have low power factor, so you're going to pay more for that voltage that motor's consuming. We get this iron saturation, which actually causes hysteresis losses, eddy currents in the rotor, or I'm sorry, the iron core. Ultimately, higher losses, which does heat the motor up, takes longer for a high voltage situation to destroy a motor than that of a low voltage motor situation, but it is still a factor that we want to consider. So if we look here at this chart given to us from US Motors that talks about the temperature affected by different loading, different voltages. So if we look at this 50 horsepower motor, if it was given nominal volt, it's normal 460 volts that the nameplate is rated at. Our temperature is 69 degrees C, and our efficiency here is 93.1. So if we reduce the voltage by 10%, then we're over here with our 50 horsepower motor. Our temperature goes up to 84 degrees C. So now we're at 15 volts higher. So our temperature's gone up. we're at 15 volts higher, so we're having that life of that motor by doing that, more than having. Our efficiency went down, and we're destroying that motor. The heat's going to be attacking that insulation and destroying it. Now, if we were to supply voltage to that motor that was higher, 10% higher than nominal voltage, then our temperature actually goes down to 62. Our efficiency goes up a little bit. So that would kind of indicate that giving it higher voltage is a good thing, because now our temperature's gone down, we're running a little more efficient. However, having a case study here of a 6.6 kV 1,000 horsepower pump motor at a nuclear power plant. The motor was being overdriven, operating at 7.7 kV. Plant engineering thought there should be no problem. Currents are well below nameplate, so it's okay, right? Wrong. What was in actuality happening was that they were saturating the iron core in the stator, causing overheating. Motor was had burned up 3 times at tune of $150,000 to repair. Thermal output of the plant reduced to 50% during that 3 to 4 weeks per repair. So the estimated loss in the electrical cells for each repair was $10 million. So the idea there of voltage being too high can cause damage to the motor. And again, it's something that dynamic testing will help you monitor. Voltage imbalance is another one. A mild voltage imbalance can create large current imbalances. That voltage or that current imbalance can be 8 times that of the voltage imbalance is creating. Again, copper heats up via I squared R losses. 10% current over current creates more than 21% heat, rapidly deteriorating that insulation. So there you see the calculation for how voltage imbalance is calculated. We're taking the max deviation from average of the 3 voltages that we measure and dividing that by average to arrive at that number. And voltage imbalance causes currents basically to circulate in the wrong direction. They're not contributing to the torque. They're basically detracting that motor. It's something the motor ended up having to overcome in order to produce the same amount of torque. Same with harmonic distortion. Harmonics are present when the waveforms are not pure sine waves. So here, if we take the blue waveform, and if there's other frequencies on that bus that repeat identically over the periods, and if we take those, like this black and yellow one here, we take the black and yellow and add it to our blue, which is the voltage that we're wanting to supply to the motor, it actually distorts the voltage, and the resulting red there is what the motor is seeing. So these are caused by nonlinear loads, semiconductor loads, computers, switching power supplies, electronic ballasts in lighting. VFDs are definitely a cause of harmonic distortion, and these cause heat. They create non-sinusoidal currents, create additional heat, causing lower efficiencies. So we don't want harmonic distortion in our power supply to our motors. Again, it's similar to, we have horsepower. If you take a horse and he's headed west, and then we tie a pig onto that horse, and the pig is traveling east. Now, does it prevent the horse from going west? No. But it's not helping that horse out at all. He's having to work harder in order to overcome what the pig's doing. So it's the same kind of deal here with voltage imbalance and harmonic distortion, causing currents that detract from torque production. So here's a case study. It was done at Shot and Paper Mill in UK. They had a large inverter-fed motor on the same bus as a smaller induction motor. So if you put the EXP onto the motor that's being fed by the VFD, Everything is fine with that motor. But then if we take that EXP, and put it on the smaller motor here, it was measuring total harmonic distortion at 11%, 9%, and 8% for the 3 phases, voltage imbalance of 3.6%. So it had a NEMA derating of 60%, which meaning that there's heat being caused in this motor due to voltage imbalance and total harmonic distortion. And what they found out was that the VFD motor running fine from the VFD, but that VFD was putting distortion back onto the bus, affecting the whole bus downstream from there. So this motor was not seeing quite as clean a power then as it should have been seen. Current issues. So why are we concerned about current issues? Well, unless you've been sleeping through the webinar, I think you've got it that current's causing heat in the motor, causing faster degradation of the insulation system. So current imbalance can be caused by voltage imbalance. It can indicate an internal problem in the motor itself. So you may not have a voltage imbalance, but you have a current imbalance. Maybe an indication of internal problems in the motor, indicating of connection issues. It can be caused by overloading. It can be caused by a light load or no load. Current imbalances are common in a healthy machines and vanish rapidly when the motor is loaded. So again, noting the loading of the motor while we have a current imbalance is important to note. Broken rotor bars are part of current signature analysis. So here we're seeing a current spectrum, and we've clipped out the part that's particular to rotor bars. And we are looking for this peak. And if that peak rises up to where our thresholds are here, then we know we've got rotor bars issue. We got a broken rotor bar issue, as we see here in the right graph, where that peak has come up and now is in the caution warning thresholds of our parameters. And so we can know rotor bar frequency because it happens at twice slip. So we know what our speed is. We've estimated that speed at least. So we know our rotor speed. We know synchronous speed because you've entered the nameplate information. We can figure that out. And the difference between synchronous speed and the speed of the rotor is slip. And twice slip is basically the frequency at which rotor bar issues, rotor bars are seen. And if there's an issue, we'll have a peak there. So it's not necessary to know the number of rotor bars here to do that kind of diagnosis. Rotor bar issues that requires constant torque levels. The next one will break sooner is kind of something that happens once we have a broken rotor bar. It stresses the other bars around it and causes those to break. Current increases there. Temperature increases. The startup process will be longer with broken rotor bars. Because of this heat increase here, of course, we're shortening the insulation life. Typically, it's not an immediate death unless your rotor does not have captured bars. If the bars aren't captured, you do risk the possibility of a bar flying into the air gap, but typically non-immediate death. So we'll get the current signature that we saw here. We also can look at our torque ripple, which looks similar to this one we see in the lower right. Looks a lot like Charlie Brown's t-shirt. So we have confirmation there in the torque ripple as well as in the current spectrum as to whether or not you got rotor bar issues. Load-related issues, process-related overloading, improper application design. You got the wrong motor installed, cavitation. You got a broken impeller, gearbox-related issues, belt-related issues can be seen in torque spectrum and the torque ripple. So here we have an example of a torque handling, air handling fan. It was a 125 horsepower motor at 480 volts, 1780 RPM motor driving an air handling fan, 6 feet between pulleys. the torque was varying 25%. So they're looking at from peak to valley here, that varying of torque would vary 25% or more. And the fan and the motor would not stay aligned. And so they were having to replace the fan pillar block bearings every 35 to 45 days. They were having to replace motor bearings every 6 months. So what they ended up doing was basically using the torque ripple, or the instantaneous torque, to determine when to realign. So when they would go out, take data, and if the torque ripple there was more than that 25%, then they would go in and realign the motor and the fan. And so they weren't having to replace bearings so often. Very simple use of it. We see another use here in the torque. This is a picture of a cavitating pump. The end bell had fallen off the end of this pump here, and so it wasn't directing the water flow. And so that's cavitation. It's a classic look of cavitation. We can tell here in the torque ripple whether load has changed in the middle of our acquisition. In that 30 seconds, the load changed here and back up, it changed again here. So things that we can tell about the process type, what's going on in the process when this happens. So load related issues. Last thing here, I think we want to look at it, startup transient analysis. We're going to look at your voltage level. Is my voltage balanced as I start this motor up? Quantify the amount of inrush current, the amount of time it takes for that motor to start. How long does it stay in that high inrush current time period there? Starting torque. And it can be used to evaluate soft starts. So here we have a case study. The customer had 6 new soft starts installed. 5 were performing as expected, but 1 was not. So what we see here on the right is the soft start working well. So we see our current come up, and it's coming up gradually as we step up the voltage to ensure a softer start. So we're not getting that high inrush current. However, 5 of them looked like that. However, 1 of them looked like this one, where we see that step up, but then bam, our voltage goes full, causing a cross the line start. Basically, we have the high inrush current at this point, and it's actually in balance. So they had quite a bit of problem there with that soft start. They were able to take this data into the manufacturer and get a replacement for that soft start to work. So static and dynamic, 2 ways of looking at a motor. They do not replace each other. They work hand in hand with each other. And so I would state that the big 5 critical motor tests would be the Kelvin resistance testing that Abel mentioned. We did talk about a little bit there. He talked about the DC testing, so it's insulation resistance testing, the Meg test, the DAPI, high pot, high voltage DC testing, the number 3 there, and 4 surge testing. Again, 1 through 4 there, we're looking at it directly evaluating the insulation of the motor. And then the 5th is to throw in that dynamic testing to evaluate the environment that motor is living in, to evaluate the power that we're giving it. What kind of quality of power are we giving that motor? And to look at the load affecting the motor. And we can see what's going on with that load and how the motor is responding to that. That gives us an insight into the environment that motor is operating in. So static and dynamic actually complement each other, can be used hand in hand. Let's say you go out, you can do dynamic much more frequently. So you go out and take data on a motor, and you find that it has voltage imbalance. So then at that point, you're going to want to correct that voltage imbalance and take that motor offline and test it directly with a static tester in order to determine how that voltage imbalance was affecting its insulation. So we'll end here with the live curve. Static testing helps us define where the insulation is on that live curve, and dynamic motor monitoring helps us determine which curve it's on. It gives us a picture of that environment and gives us a chance to correct the behavior, correct that environment, so that we're sending that motor on to a better curve. So at this point, I would entertain any questions.
All right, awesome. So since we've wrapped up the presentation portion of our second segment, we're going to jump into the Q&A session real quick, but right before that, for those of you that are leaving, if you could please take a few minutes to answer our survey at the end of the webinar. It'd be really helpful for us to see how we can improve upon our future seminars. If you have any questions, please submit them now to the Q&A box on the right side of your screen. Before we get into the last few questions though, I would like to remind everyone that a copy of these presentations, certificate of attendance, your motor product discount code, and a link to the video recording of this seminar will be emailed to everyone in about 2 business days, but I'm going to try and aim to have that out tomorrow morning before our second session. So, jumping right in, I'm going to ask our first question of our second Q&A session to Abel. Abel, can these devices be applied to VFD controlled motors?
Yeah, okay, thanks, Michael. Yeah, definitely. The device that that Leslie has been showing, I believe, is the EXP4000 dynamic motor tester. It's the one that shows up in the screen right now. And definitely, you can use it to test a motor connected to a variable frequency drive. Leslie, I believe, showed a couple of slides there where you had the device connected on one side of the VFD, between the VFD and the motor, and then you had the device connected on the other side of the VFD, essentially on the mains that feed that VFD. You can do comparisons between the voltage injected into a VFD and the voltage that the VFD is supplying, between the currents that go into the VFD and the currents that go out of the VFD. You can find problems in the motor provoked by the VFD, and you can also find problems in the VFD itself, given the capabilities that the device has. So to answer your question, yes, it can definitely be applied to motors connected to or controlled by a voltage frequency, or I'm sorry, a variable frequency drive.
Thanks, Abel. While I have you, the second question is also going to be directed for you. With this method, is it possible to replace vibration monitoring?
Well, that's an interesting question. You can detect a lot of the issues that you can detect with vibration monitoring using this method. We use something called torque signature analysis, which essentially is using the currents and the voltages that are fed into the motor, and doing a Fourier, or a type of Fourier analysis on those currents and voltages, allow us to find all the frequency components of the voltages and currents. So we can find a lot of the problems that you can find with vibration monitoring, but you cannot find all the problems that you can find with vibration monitoring. So I would say that they can both complement themselves, because you can also find problems with this that you cannot find with vibration monitoring. So I would say that this tool and the tools associated with vibration monitoring intersect, but they cannot be each replace each other. All right, so I would say that this is a complement to vibration monitoring that expands the amount of information that you can get out of the motor, and the amount of predictions that you can make on the life of the motor, and then it improves the maintenance program that you can do on those rotating machines. Okay.
All right, thanks. Back over to Leslie. Does Megger have an online test similar to PDMA testing?
So, yes. I think PDMA actually puts theirs in the same box. They do have the option anyway to put it in the same box as their static testing, whereas Megger's is separate, two different boxes. But the online test, in fact, the one that you see on the screen now is the EXP4000, and it comes with of course, the voltage and current sensors to do the testing with, and also presents with the same kinds of parameters as that of PDMA. So online testing of power quality type stuff and spectrums. However, I don't believe they have the torque element, which we do have the torque ripple and instantaneous torque, which is again key to identifying mechanical issues through voltages and currents.
All right, thanks. Back over to Abel. Abel, why does overvoltage cause a reduction in temperature?
Well, that's an interesting question. The first thing to know is that motors are typically designed to operate with a plus minus 10% or within plus minus 10% of rated voltage. So, and also that ideally you should not operate the motor with a difference to the rated voltage of more than plus minus 2%. I mean, even though you design them to operate within plus minus, you should not ideally operate them within plus minus 2%. Those are ideal conditions that are very hard to realize in a factory. Now, when you increase the voltage of the motor, what happens is that the full load current of the motor will drop with every percentage of increase of the voltage of the motor. A decrease in the full load current will mean that you have less heat generated by the Joule effect on the resistances of the windings, and therefore you will have a smaller or lower temperature rise. That's the answer to that question. However, it is a very bad idea to operate the motor at a voltage higher than nominal regularly, because typically motors are designed to operate with maximum efficiency at voltages similar or very close to the nominal voltage, and also because when you operate a motor at a voltage higher than the nominal, the power factor of the motor will drop, meaning that you will be affecting not only the motor itself, but you will be affecting every element of the same, let's say, chain of or connected to the same mains that you have the motor connected to. So even though, again, you can operate motors at voltages higher than nominal, it should not be a condition that you want to keep for a very long time. Okay.
Great, thanks, Abel. So Leslie, what is the acceptable limits of harmonics, current unbalance, and other dynamic test values as per international standards like IEEE?
So we do use IEEE where it does talk about limits and gives us standards there on our on our parameters. So for harmonic distortion, we're looking at total harmonic distortion, which means that we are not taking individual individual harmonics and giving you those numbers. We're basically adding them all up to give us that harmonic distortion. So there we're using that as I believe the caution level is at 7 and warning level at 9. Again, that follows and looking at IEEE standards. Current imbalance is set at 10% for a warning or caution. No, caution, and then 120% of current would be a warning level on those. On voltage, we do 110% or 120% as far as caution and warning. On the underside, we're less generous. We do the 95% under voltage or 90% under voltage would give you warning levels. So we do shorten that a bit. And all of these are adjustable to whatever limits you want to put in. So So it is adjustable to being able to put your own limits in if you don't like ours, or there may be specific reasons why you may want to set for a particular motor a different threshold, because you know this motor is always, let's say it's got a porosity in the rotor and always shows up as a rotor bar issue, but it's porosity. So you may not want to always see that warning, so you can change that level for each of the parameters.
Thanks, Leslie. Abel, how does voltage unbalance affect the motor?
Okay, that's a very good question. Voltage unbalance in the first place creates a negative sequence component on the voltage system. The negative sequence component on the voltage system has a rotation, a phase rotation that goes counter to the regular or the rotation of the positive sequence component, which would be related to the main voltage sequence that we have. What that means is that the voltage unbalance itself will create a counter torque on the machine, and that counter torque will be rotating against the torque of the machine at a frequency that's twice the frequency of the rotor, because it will be rotating in the opposite direction. So it will be rotating, let's say, at 60 hertz in the opposite direction, but the rotor itself is rotating in the opposite direction. So you have a system that's rotating in the opposite direction at twice the frequency of the rotor. That in itself will create vibrations in the operation of the machine. However, the most damaging effect of voltage unbalance is the fact that it will create current unbalances in the rotor that are way higher in terms of the percentage of unbalance than the percentage of unbalance of the voltage unbalance in the stator. What that means is that you will have a magnified effect, if you want, on the current in the rotor, which is very damaging for the machine. The counter torques created can break rotor bars. They can create oscillations depending on how high the percentage on balance is. They can create oscillations, and they can create a lot of heat circulating in the rotor, and over time they will lower the life of the machine very, very much. Okay, I guess that answers that question.
All right, thanks. Next is over to Leslie. Leslie, which type of testing is more important, static or dynamic?
So, good question. However, I hate having to choose one. So I believe that static and dynamic are both very important. They give you different aspects to look at. But if you're having to choose because, hey, I only have money for one of the technologies, then I would take a look at the motors that I'm trying to test. Do I have brand new ones? Is this a new plant that I now have new motors in? Or is my plant 40 years old and I'm trying to keep old motors running, or I really have no idea what I got? So if I'm in that situation, I have no idea what I've got out there, and I've got an old motors, old plant, then I probably would go for static testing first. That way I can assess the state of the motors that I have, and do some work as I identify motors that are weak, that are less than reliable, and replace those. I would use static testing in that situation. If I have a brand new plant, brand new motors, then I would probably choose the dynamic testing, because I'm making assumption there that my motors are starting out good, and I want to assess my environment that those motors live in, and that would give me warnings then, like such as voltage imbalance or distortion or overloading type answers. I know what's going on with the motors, and as it ages, then I would start bringing in the static piece. Again, kind of depends on your situation and the motors that you're wanting to test. Michael?
All right. Thanks a lot. Over to Abel. Do I have to know the number of rotor bars for rotor spectrum testing?
Actually, you don't. The more information you have about the motor that you are testing, the easier it would be for you to interpret the results you're getting. So if you know the number of rotor bars, then it's better for you. You have that information in your hands when you are analyzing the results. But the results that you get do not rely on knowing that information. Because what the machine, what the instrument does is it senses the currents and voltages, and remember that it uses the induction motor as its own transducer, because anything that happens in the rotor of the induction motor is reflected back into the currents of the stator, because the load takes power from the motor via the rotor. Now that power is taken from the electromagnetic flux that's created in the air gap. Now that electromagnetic flux is created by the circulation of currents in the windings of the stator, and the amount of current and the form that current takes depends on the form of the torque that's been drawn out of the machine. So from what I'm trying to tell you is that everything that happens in the compound made by the load, the rotor, and the power source is reflected into the voltages and currents that go into the stator. So what I'm trying to get at is that you don't need to know the number of rotor bars, because the analysis that's done will give you frequency components and they don't need to know the number of rotor bars. Of course, if you know the number of rotor bars, you can use that information, to realize that there may be a problem here that otherwise you would not be able to, interpret properly. I would say, all right, but it's not necessary to know the number of rotor bars.
Alrighty then. Back over to Leslie. Are actual motor parameters such as stator resistance and reactance essential for accurate dynamic analysis?
So it is important. Nameplate information is important to us. So knowing the voltage of the motor, the horsepower, the amps of that motor are all very important properties to know. Nameplate speed. So technically we need horsepower or kilowatts, the voltage, speed, current of that motor, and if it's not a VFD, whether that nameplate information is for a 60 hertz motor or a 50 hertz motor, is essential for being able to interpret the results. We actually use that nameplate information to estimate speed. We use that nameplate information to estimate the torque and derive torque from the voltages and currents. Now, other things that help us become more accurate at the information we're giving you would be lead resistance. So if we knew the lead resistance of the application under test, then we can be more accurate at the voltage drop that occurs from where we're sensing voltage to what the motor actually is seeing. So again, we can be more accurate if you give us that lead resistance, and if you give us stator resistance, which you can find from your static testing. You can give us stator resistance there. So if you enter those two values also, then we become a lot more accurate at our assessment of voltage and currents in everything. Actually, it depends on that. Our speed estimate especially becomes more accurate. This instrument, the EXP4000, was actually invented to go after efficiency measurements. And so if you're actually hunting down efficiency information then giving that lead resistance and stator resistance becomes very important. I believe
All right.
that's it.
Cool. Excellent. So it looks like we've run out of time for questions. We apologize if we didn't get to yours live, but we will try and follow up with you offline in the following week to give your answers the attention that they deserve. I'd like to thank you all for attending. If you could, please remember to answer the survey. That survey will include a field for you to request a demo or if you're interested. As a reminder, your follow-up email will be going out shortly with the motor promo discount code. And for those of you who stuck around, that word is motor. You can drop that like trying to get into a speakeasy and it'll give you 10% off select motor products. But once again, I'd like to thank you all for attending. I hope to have you join us tomorrow for our second day of the Virtual Motor Best Practices Seminar. If I don't see you then, I hope you all have a great week and thank you all for attending today.